without hurting the estimation at the tail of the distribution. Okay? So I remember you also asked me, what if there wasn't a mechanism for uniform vertex sampling? Okay. So if there is no mechanism to do that, then we better not perform random jumps, otherwise we're not going to know the probability of observing a node, so we cannot remove this bias. So let's assume no random jumps. Clearly, the hybrid estimator is going to do worse than the original one because it assumes the initial Walker locations correspond to uniform vertex samples. If that's not the case, then it's going to be outperformed by the original estimator. So let's focus on the original estimator for the purposes of this talk. So to investigate this, we're going to initialize, in some simulations, I'm going to initialize the Walkers in proportion to the degree, okay? And some others I'm going to initialize in proportion to the reciprocal of the degree as alternatives to, in the case where I don't have uniform vertex sampling. So we observed that the results for both types of initializations are worse than for uniform initialization. And in particular, when we initialize in proportion to the degree, is especially worse. And that's because when you initialize in proportion to the reciprocals, that's closer to the uniform distribution. So the takeaway message that we get from the results is that when you can't do uniform sampling, when we look at the graphs, it makes more sense to use fewer Walkers. But it's not clear that you should use only one Walker, because if we're not performing random jumps, we might be as well trapped in one component. We might not see other components of the graph. So more work still has to be done to quantify exactly how many Walkers you should use. So the contributions of this chapter are as follows. We propose a new method, directed unbiased frontier sampling, that generalizes previous methods. We introduced the hybrid estimator. We investigated the impact of parameters on estimation errors in order to propose practical guidelines. We showed that DUFS exhibits similar or better performance than previous methods. And this work is ready for submission. We're going to send it to the ACM transactions on knowledge and data discovery soon. Okay, so this brings us to the second chapter, which regards the characterization of large networks, specifically degree distributions, when we perform independent edge sampling. Okay. So as I said, I'm just going to summarize the results. We formulated this problem as the more general set size distribution estimation problem, and used Fisher information to quantify the statistical information in a sample, and then apply the Primero bound to derive estimation error lower bounds. We show that for large networks, there exists a sharp threshold with respect to the fraction of sampled edges. If this fraction lies below the threshold, then distribution statistics such as the fraction of nodes that have a particular degree or the average degree are essentially unrecoverable. For power law, that means power law graphs, that means that we need to sample more than 50% of the edges. So we showed that the maximum likelihood estimator achieves the error lower bound if the fraction of sampled edges is above the threshold. This work was published in the Journal of Selective Areas and Communications. So now we're going to go to the third chapter, which, do you have a question? No? Oh. So on the selective harvesting over networks, in which we want to answer this question, that is, how to find target nodes efficiently, how to find nodes that have a given characteristic in a network in an efficient way. So to illustrate that more abstract problem, I have a specific example where we want to find researchers that have been cited between A and B times in the last 5 years. So you could use the website Semantic Scholar to perform a search like this. This is a project where Andrew McCallum is involved. They automatically generate profiles for researchers, and you can see their publications, the number of citations in the last few years, and their collaborators, and also who are the influencers and who they influence. It's a really cool website. So you can start from a node that satisfies this query, okay? And then you see the collaborators of this researcher, which we're going to call the fringe nodes because these are at the fringe or at the border of my observed graph. All the other nodes are unknown, as well as their connections at this point in time. So the way you can perform the search is essentially take a fringe node and check whether it's part of the target population, and in this case it was not. But I also learned about new fringe nodes. Okay, so in the search goes like this, and you keep querying or visiting new nodes and expanding this fringe or border set. So ideally, we would like to take into account the labels, these sort of positive or negative labels that we see in order to guide, to drive this search in a more efficient way. But traditional graph search algorithms, such as BFS or BFS, just cannot take that into account. They have a specific way in which they sample the nodes. So that's why we say they're inefficient for this problem. Other applications for this type of search include investigating people suspecting of fraud in the IRS. So you can, after checking the background of checking one individual, you can decide, you can look at this person's connections and decide who to investigate next. Because this is an important problem, other people have thought about ways to solve it. And in particular, heuristics have been proposed for this problem and related problems since 2012. Most of these heuristics are based on some notion of homophily, this idea that, this assumption that the target nodes seem to be connected with other target nodes. Okay? So none of these methods can take attributes into account. So if you know, for example, that this researcher was advised by someone, where he went to college, where he got his PhD from, and his age, perhaps you can learn the existing correlations between these attributes and the labels of the fringe nodes. Since the natural way to do that would be to use a machine learning method, or more precisely classifiers for supervised learning problems. And that, in our case, the data is the observed network, which we have to represent as features somehow. The problem of designing features is interesting per se, and I explained some of the features we designed in the proposal. So today I'm just going to say that it can be roughly categorized into purely structural, label and structural blends, and attributes and structural blends. So once we have this design matrix where its rows represent different individuals and the columns represent features, we can take the labels, the observed labels, and fit a model from this matrix and this vector 1. So we estimate parameter state of this model, and we can use that to essentially rank the fringe nodes according to how likely they are to be targets. Once we do that, we're going to query the node that is most likely to be a target in sort of a greedy approach. And that observation can be used to, can be added to my design matrix and to my vector y, so that I can update the model parameters and keep querying new vertices. So are these types of data-driven models really better than the existing heuristics? That's a question that we needed to answer. And in order to do that, I took these existing heuristics or one of the data-driven models and a data set that is essentially a network consisting of nodes that have some sort of attributes. These attributes are typically binary, so one of the attributes was used to define the target population. Okay, so nodes that have that attribute are targets. And then I simulate the search using heuristic or the model on this data set and count the number of targets found after a given number of queries. Okay, so I'm going to fix the number of queries. And in fact, I perform this many times repeating at different target nodes and compute the average number of targets found as the performance metric. So this table summarizes the results obtained on 5 data sets indicated in different columns. And the first 4 rows are the existing heuristics, and the following rows correspond to these sort of data-driven models. So we in particular use the logistic regression, random forest, exponentially weighted least squares, support vector regression, and ListNet, which is a method that comes from the learning to rank literature, which was something that Ben told me to look into during the proposal. So the cells here are essentially the average number of targets found after this number of nodes was queried. And so the larger this number, the better. What we see is that for each data set, the best method, so the best method varies across data sets. That's pretty much it. But what is more concerning is the fact that the method that works best on one data set can also be the one that is the worst on another. And the problem is that we don't know the performance of a method on my data set until we actually go and try to execute this task. So ideally, I would have an oracle or a crystal ball that would tell me, well, this is the best method on this data set. But we're going to show that the best method is not necessarily optimal. I know it sounds contradictory, but consider the simplest way of combining different methods, which is alternating them in a round-robin fashion. So here's what we're going to do. We're going to take a couple of set of methods, let's say represented by the Greek letters theta, gamma, and phi here at step D. And I use the first method to make predictions about my fringe nodes and decide which node is more likely to be a target. So let's say I recruit this one, I query this node, and I observe that it was not a target. I'm going to use that to update my model of my method's parameters. And these are the parameters at step T plus 1. So next, I'm going to use the second method to decide which node to query. So this one was a target, and again, I'm going to update the method's parameters. And in round robin, is now going to use the third method to decide which node to query. Okay, so we can keep doing that, updating the model parameters, and go back to the first, second, third, and so on. This is what round robin does. How does it perform? So here I have the same table as I showed you before, and I'm going to take 5 methods, sort of arbitrarily. It could have been other methods, but these ones tend to perform well on average, and alternate them using this round robin policy. And what we see is that for example, for this last data set, round robin outperforms all the other methods, including the best method for that data set. And what is surprising is that round robin is not only using random forest, but it's also using MOD and ListNet, which are methods that do not perform well on this data set. Okay? And you can see something similar for other data sets as well. What's going on? We need to understand that in order to propose a method that's going to work well. So we show empirical evidence that round robin explores regions containing more targets likely to be scored high by a method. And we also show that round robin obtains more diverse training data, causing models to generalize better. In other words, diversity is a key ingredient to better performance. Note that this diversity cannot be obtained by querying nodes at random. So if you use a single method, let's say support vector regression, and every now and then you decide to query a node at random, if the target population is small, it's very unlikely that that node is going to be a target. So this is going to hurt your overall performance. Moreover, if the method that you're using had already predicted that that node is very unlikely to be a target, it's not going to change the parameters, or that observation is not going to change the parameters of your model significantly. It's not going to improve it significantly. That's why we say that this diversity must be directed. We need to have these different methods, each one with different opinions or perspectives about which node should be queried next, in order to mitigate this effect that is observed when you have a single model. the effect, the sort of inbreeding effect that keeps recruiting the same types of nodes and doesn't learn about the big picture. So clearly, round robin is not the best we can do, right? It's the simplest thing we can do. The generalization is to allow us to choose any method at each step. To some extent, we want to choose the best methods more often, but at the same time, we want to keep using the other one so that we don't break diversity. And note that we don't know what are the best methods, so we have to learn that. And that sounds pretty much like a exploration trade-off that we see in multi-armed bandits. So we model selective harvesting as a multi-armed bandit. In this slide, I'm just going to give an overview of what a multi-armed bandit is. So these are sequential decision problems where a player has to choose among k actions, or arms, doing n turns. This is typically illustrated by k casino bandits, and each one is associated with some unknown reward distribution. So in each turn, the reward, nature draws a reward from the unknown distribution associated with each arm, and that reward is kept hidden from the player. The player pulls an arm, and then observes the reward associated with that arm. The player's goal is to maximize the accumulated reward, right? And so if you think that in the case where these rewards are IID draws from the reward distribution, then the player's goal is to learn what arm has the largest expected reward. Okay, and so in some sense he wants to converge to the best arm. But our problem has many differences with respect to this classic MAB. In particular, in selective harvesting, the set of actions, which are the fringe nodes we can query, change at each step. So the way to circumvent this difference is to model methods as arms. Once you select a method, then the action is uniquely determined by that arm. Essentially, the method is going to tell you should query this node. In that case, someone would say that this is a stochastic multi-armed bandit, and that there are lots of algorithms to do that. The most popular ones being UCB1, UCB normal, Epsilon 3D, and Thompson sampling. So, but there is another difference, which is the reward distribution is changing over time. And that's for two reasons. One, we are updating the model parameters. And two, the set of fringe nodes is changing. So the set of possible rewards is changing. So again, one could say then you have a multi-armed bandit with non-stationary reward distributions, in which case you could use, let's say, dynamic Thompson sampling, which is based on the same ideas as Thompson sampling. But our goal is not to converge to the best arm. If we do that, then we break this principle that I talked about at the previous slide. So the solution that we come up with is to adapt dynamic Thompson sampling to prevent the variance of the distribution associated with each arm from shrinking too much, so that we keep exploring the other arms. And that gives rise to the method that we call directed diversity dynamic Thompson sampling, or DQTS for short. So here I'm gonna show you how this method performs on the Sightseer data set, which is essentially where nodes represent papers and undirected edges indicate that a paper has cited another. The target population here is the set of papers that were published on NIPS. So in the y-axis, I'm going to show you the number of targets found, the accumulated number of targets found up until this point in time that is measured using the number of, according to the number of queried nodes. So the blue line here is the performance of round robin. The other solid lines are the individual models. Note that these models are also used by round robin and DQTS, that is shown as the orange dashed line. And what we see is that I forgot to mention that all these curves are normalized by round robin's performance, and that the shaded area represents 95% confidence intervals for the mean. So what we see is that both round robin and DQTS outperforms all the other methods to the point, and that DQTS consistently is still better than round robin. And that observation is consistent across other data sets. We